Hello, AP Statistics students, and welcome to the College Board virtual instruction for AP Statistics. My name is Luke Wilcox. I am an AP Stats teacher at East Kentwood High School in Kentwood, Michigan. My colleague, Brendan Murphy, and myself have taken you all the way through all of the content that will be covered on the AP Statistics exam at this point. And this week, we are dedicating to big review ideas. And I'm very excited about the topic of today's lesson. It is my favorite topic in AP Statistics and what I call the holy grail of AP Statistics, and that is the p-value. So I hope that by the end of today's lesson, you have a different understanding and a better understanding of the p-value. So let's go ahead and jump right into things here. Quick check to make sure that you are in the right location. This is AP Statistics. My name is Luke Wilcox. A couple of quick announcements to get started here in case we have anybody that is new that is joining us. We are meeting on a daily basis, 2 o'clock Eastern Standard Time, Monday through Friday. As I mentioned before, we have finished the review of the specific content, and what you're going to be seeing this week are what we're calling general review strategies, sort of some big idea type things. And then next week, very specifically dedicated to doing some practice FRQs that should prepare you for the AP exam, which is May 22nd for AP Statistics. So any of the resources that you might need for these lessons, you can download at statsmedic.com/YouTube. You just look it up by the date and you should find downloadable PDFs of the lesson as well as the homework problem. So speaking of homework problems, Mr. Murphy gave you a homework problem yesterday. It was a multiple choice question from a previous exam. So we're going to start by checking in on this multiple choice before we move into anything new for today. So here's what it says. When using a one sample t procedure to construct the confidence interval for the mean of a finite population, a condition is that the population size be at least 10 times the sample size. The reason for this condition ensures that. Okay, before I even look at the answer choices, I'm going to take this condition and state it in a different way. I'm going to put it in the reverse order. Instead of saying that the population size is at least 10 times the sample size, the other way of saying that is to say that the sample size is less than or equal to 10% of the population size, which is maybe the way that you saw it in your course. So the 10% condition is what we're talking about here. And what we want to know is why is it that we actually check the 10% condition? And just to remind you where this first showed up, it showed up with binomial distributions when we were checking the 4 conditions that are necessary in order to say that a distribution is binomial. And the second condition is the independent condition. And what we said here was that if you are sampling without replacement, then we have to check the 10% condition to be sure that one trial is independent of the next trial. In other words, knowing the outcome of one trial does not change any probabilities or give us any information about the next trial. So we know that the 10% condition has something to do with this idea of independence between the trials. Now, let's look at each one of the answer choices and see what we have here. Okay, answer choice A, the sample size is large enough. Now, that is a condition that we'd like to be met in order to use a one sample t procedure, but it's a different condition. That's what's called the large sample condition. So that one's out. Choice B, the central limit theorem is applicable for the sample mean. Well, that's actually still part of the same condition that I just mentioned, the large sample condition. If we have a big enough sample size, the central limit theorem says that the sampling distribution is approximately normal. That's not what we're going for here. And now I'm actually going to take us down to choice E. The sampling method is not biased, which is very important, but that's part of a different condition, which we call the random condition. And so we are left with only 2 choices here. So let's look at each one of them. Answer choice C says that the sample standard deviation is a good approximation of the population standard deviation. Well, for this, we'd actually want our sample size to be bigger, not smaller. We wouldn't want it to be less than 10% of the population. It would actually be best to have the biggest possible sample size there. So this one's incorrect, and I'm hoping that answer choice D says what we need it to do too. The degree of dependence among observations is negligible. Well, that's exactly what we were talking about here way back in the binomial conditions. And so answer choice D is the reason why we check the 10% condition. So hopefully you did okay on that practice problem. And I think we are ready to jump into today's big topic. So I'm going to start with a lesson overview where I'm going to provide you with a couple of learning targets. And then at the end of the lesson, we'll come back to those learning targets and make sure that we got what we needed to. So there are two of them. And of course, as mentioned, both related to the p-value. And so the first one says, understand how to calculate a p-value for a significance test. And the second learning target, which I think is the more important learning target, is to be able to interpret a p-value for a significance test. And then, of course, be able to use that p-value to make a conclusion for a significance test. So I'm going to say right here that this is the big goal of today's lesson, to be able to interpret a p-value so that we can make a proper conclusion. So let's go ahead and jump into today's activity. So I've called the activity tracking the p-value through AP statistics. And the idea is that the p-value, while you learned it formally at the end of your AP statistics class, chances are you had been developing your thinking and understanding and reasoning about the p-value all the way throughout the course. And so what I've done is I've put together 4 example problems that would come from 4 totally different parts of the course. One from the beginning, one from towards the early on, a little bit later, and then one towards the end. And we're going to see how our progression of understanding of the p-value happens throughout the school year in AP statistics. So let's start with this awesome quote that I got from Wikipedia as I was preparing for today's lesson, which says, the term Holy Grail is often used to denote an elusive object or goal that is sought after for its great significance. And listen, the p-value in AP statistics is exactly that. It is the Holy Grail, right? It is the often elusive object, the thing that we are trying to understand, and ultimately like what we're working towards for the end of the year is to be able to understand the p-value. I also very much appreciate that this quote just happened to have the word significance in it. So the goal of today is not to have some memorized thing like, if the p-value is low, then we're going to reject the null hypothesis. That is not the goal. The goal is to understand what that p-value is telling you. What is the interpretation of that p-value, which ultimately will lead to your conclusion to reject the null or fail to reject the null. But I just want to make sure that we have a proper understanding of the p-value. So we're going to start with number 1 here. And this comes from an awesome lesson that AP Stats teacher from Pennsylvania, Doug Tyson, all-star AP Stats teacher, created this lesson and is one that is very commonly used throughout the country. So there is a good chance that you may have even seen this example in this activity in your own classroom. So here's what it says. Joy Milnes participated in an experiment in which she correctly identified 11 out of 12 shirts by whether or not they were worn by Parkinson's patients. To investigate if Joy can smell Parkinson's, an AP Stats class simulated what the results might be if Joy had been simply guessing on all 12 shirts. Here are the class results. So a little more detail about the experiment. Joy Milnes claimed that she could smell Parkinson's. And so experimenters set up an experiment with 12 t-shirts, half of which had been worn by Parkinson's patients, half of which did not have Parkinson's. Then they gave the shirts to Joy, she smelled them, and then she tried to identify whether they had been worn by a Parkinson's patient or not. And it turns out that out of the 12 shirts, Joy was able to correctly identify 11 of them. So we've got a couple of questions to get us started here. The first one is the claim. And this is the claim that we're going to assume to be true in order to carry out the simulation. And for the simulation, the stats class wanted to know what would happen if Joy just simply guessed on all 12. She couldn't smell Parkinson's. She just totally guessed on all 12. So the claim here is that Joy was just simply guessing. And the other way of saying that if she was just simply guessing, that means that she can't smell Parkinson's. All right. Now the statistic is the observed result that you get from the sample or from the experiment. Well, in this experiment, the observed result was that Joy got an amazing 11 correct out of 12. Now, the next question is, does this provide some evidence that Joy can smell Parkinson's? Well, definitely, right? 11 out of 12 is really, really good. If she were simply guessing on all 12 of them, we would expect her to get about half of them right. So certainly 11 is much better than if she had just simply guessed, where we would expect her to get 6. So we do have some evidence that Joy can smell Parkinson's. The next question is whether we have convincing evidence. And in order to answer that question, we have to have a p-value. We have to know how likely is it that we could have seen this observed result purely by chance. Then we can make a decision about whether or not we have convincing evidence. So we are going to use the dot plot here in order to estimate our p-value. And we just have to understand what each one of those dots represents. So for example, this dot that you see here at 8 means that that student in class did a simulation. So they could have maybe tossed it 12 times and tried to guess whether it be heads or tails. Or maybe they had little cutouts of t-shirts. Half of them said Parkinson's, half of them said no Parkinson's, and somebody had to simply guess what each one of the 12 was. And for this particular simulation, out of the 12, that person guessed 8 correct just purely by chance, by guessing, right? And right away, you'll notice that at the very center of the distribution is 6, which is what we would expect if somebody was just simply guessing, that they would get about half right. Now we know, because of sampling variability, that it might be a little bit higher than 6. It might be a little bit lower than 6, which we see in the dot plot here. So the next question then is, how likely is it that we would get Joy's result? Well, let's make sure that we clearly identify that here. And Joy's result is this right here, the 11. And that's what I'm going to call the statistic. That was the observed result from the experiment, right? Now, remember, one thing I want to make note of here, this simulation was done assuming that this claim is true. In other words, we created this dot plot by assuming that Joy was guessing. These are the possible values that we might get when Joy is guessing. Well, how many times did the class get that 11 or better, right? If 11 is convincing evidence, then 12 would also be convincing evidence. But we see here that 11 or higher only happened one time, and there are 30 dots total there. So that is going to allow us to make an estimate of what the p-value. And I'm going to say approximately here because it's an estimate, which is 1 out of 30, or about 0.03. Very, very unlikely to happen purely by chance. So let's go ahead and see if we can interpret this p-value. And when we're interpreting the p-value, I'm trying to interpret what this 0.03 is telling me. So to start the interpretation, I need to make note of what we assumed to be true up front. So that's the first part of the interpretation, is to say that we were assuming that Joy was guessing. And so assuming that Joy was guessing, there is about a 0.03 probability that she would get 11, and let's be careful here, 11 or more, could have been 12, even though that didn't happen in the dot plot, that she would get 11 or more correct purely by chance. Now, that is a very, very low probability, which is suggesting to us that maybe the assumption that we made up front is not really true, and that we have convincing evidence for the other claim, which is that Joy can smell Parkinson's. So because this p-value is so small, so unlikely to happen purely by chance, we do in fact have convincing evidence. So I'm going to say here, yes, we have convincing evidence because the p-value, which is very small, 0.03, is less than alpha, which I'm just going to use 5% as our alpha value for all of the problems that we're going to go through today. So based on the observed outcome of 11 out of 12, we do in fact have convincing evidence that Joy can smell Parkinson's. Side note, the 12th one that she got incorrect, she had said that person had Parkinson's and that person did not have Parkinson's. But several weeks or months later, that person did in fact develop Parkinson's. Crazy story. You can look it up on the internet. All right, let's move on to question number 2. And there's a new scenario here, and this would likely be a little bit later in the course, whereas the Joy Parkinson's activity you might have even done in the first week of school. This is something that you would have done several months later. Okay, so here's what it says. According to YouTube Analytics, 30% of all AP Stats students are using YouTube as part of their AP exam review. College Board believes the true percent is higher and selects a random sample of 80 AP Stats students to survey. In the sample, 32 students were using YouTube. Okay, let's think about a couple of things here first. The first thing to identify is that the thing that the College Board is measuring is the number of students that are using YouTube here. Okay, the number of students. That's like the number of successes in a fixed number of trials, which is 80. And I'm hoping that's triggering to you that this is, in fact, a binomial distribution. Now, just to make sure, we know that there are 4 conditions that are necessary for this to be considered a binomial distribution. So let's just check those real quick. Okay, for B, each trial is binary as either a success or a failure. Well, a success here would be that the person's using YouTube, and a failure is that they are not. So that condition is met. For the independent condition, a couple of things to think about. First of all, it is a random sample, so that should help us with independence between each trial. And then again, we do have to check the 10% condition here because we're sampling without replacement, but certainly 80 is less than 10% of the population of all AP Stats students. And so we would say that the I condition is satisfied. N says that there is a fixed number of trials. Well, sure, there's a fixed number of trials. The sample size is 80. And then S, we need the same probability of success for each trial. If we assume that the YouTube analytics are correct, then the probability of success for each trial would be 0.30. And so all 4 conditions are satisfied, and we know we have a binomial distribution. Now, one thing that I hope you remember about binomial distributions is how to calculate the expected value, which is just n times p. So in this case, 80 times 0.30, which is telling us that we would expect out of the 80, about 24 would say that they use YouTube, right? So let's move into our next set of 4 questions here. The first question says, what is the claim that we are trying to find evidence against here? Well, the claim is the YouTube claim that they made right up front, which is that 30% of AP Stats students are using YouTube. So the claim is 30% of Stats students are using YouTube. And the College Board wants to try and collect some evidence against that claim. So they did, and that's where we get our statistic, which is the observed outcome from the sample survey. And what we got there was that there were 32 students that are using YouTube. So the next question is, does this provide some evidence that the true percent is higher than 30? Well, we know that if 30 is true, we would expect to get about 24 successes out of the 80, and we got 32. So certainly 32 is bigger than 24, and we do have some evidence to suggest that the true percent is higher than 30%. So the follow-up to that is, do we have convincing evidence? And once again, in order to answer that question, we need a p-value, which will tell us how likely is it that we could get this result or more extreme purely by chance. So let's take a look at the distribution here. And one thing I want to make note of is the fact that we have to assume that this claim is true in order to make this distribution here. So we're going to assume here in this picture that 30% use YouTube. That had to be assumed in order to create this distribution that you see here, right? So this claim is assumed to be true. Now you can actually see that because if you look, the value right at the center of this thing is 24, which is what we would expect if the 30% claim is true. Now, the next thing we need to identify is where our statistic is in this distribution. And it's 32, so I'm going to look here, and I see 32 is right about here. That is the statistic that the College Board got when they took their sample of 80 students. So in order to calculate the p-value, we want to know how likely is it that we would get that observed result or farther from what's expected purely by chance. So not only do we want 32, but we want 33 and 34 and 35 and 36 and all the way up, right? This right here is going to give us our p-value. And if you recall from when we were studying binomial distributions, this is one of the cases where we would use the calculator to help us to find the probability of 32 and 33 and 34 and so on. The trick is to use binomial CDF on the calculator. And we are going to have to use the complement rule as well, because we want the values 32 and higher. So we're going to subtract out the values 31 and lower. So I'm going to do 1 minus binomial CDF. And the commands that we would need here in the calculator is the number of trials, which is 80, the probability of success for each trial, which is 0.30, and then the number of successes, and we want to subtract out 31 and below, which would leave us with 32 and above. So if you plug that into your calculator, you're going to get a p-value of about 0.036. That's our p-value. So I think we are now ready to try and interpret that p-value, and I'm going to try and use a similar interpretation as we did in the Joy-Parkinson's example. And I'm going to start out with the claim that we assumed to be true. So we're going to say, assuming that 30% of AP Stat students use YouTube. And then we want to try and interpret this p-value here of 0.036. So we're going to say there is a 0.036 probability of getting. Now let's look at our picture here, and our picture says 32 or above. That's what we have shaded in purple here. So it's a 0.036 probability of getting 32 or more who use YouTube in a sample of 80 purely by chance. Now, just like the Joy-Parkinson's activity, we've got a p-value that is very small here. It is very unlikely that we would get this result, assuming that that claim was true, which is telling us that this claim, we have some evidence against that claim, and convincing evidence for the alternative, which is that the true percent is higher than 30%. So once again, do we have convincing evidence? Yes, we do have convincing evidence, and that's because the p-value is small, 0.036. Specifically, it's less than our alpha value of 0.05. So that takes care of number 2. And I think we are ready to move into the more formal significance tests that you started seeing towards the end of the year in AP Statistics. So let's go ahead and jump to number 3. And let's take a look at the context. Here's what it says. Mr. Wilcox believes that 12 hours of preparing is needed to prepare for the AP Statistics exam. A random sample of 20 AP Stat students from last year revealed a mean of 11.4 hours spent preparing with a standard deviation of 3.72 hours. Do the data provide convincing evidence that last year's students spent less than 12 hours preparing on average? Assume the conditions are met. Okay, now that we're into the more formal significance test that you saw towards the end of the year, I think we can officially write a null hypothesis and an alternative hypothesis for this one, okay? So the null hypothesis is going to be the claim that's made right up front by Mr. Wilcox that it takes 12 hours on average to prepare for the AP exam. So I'm going to make sure I'm using the correct notation here for the population, which is mu, and say that that's equal to 12. Now for the alternative, we have to look at the wording of the question to decide whether it's one-sided or two-sided. It says very clearly here that we're looking for evidence that it was less than 12 hours. So that tells us our alternative hypothesis is going to be mu is less than 12. Now, anytime you're writing out your hypotheses, you need to make sure that you clearly define what your parameter is here. And I'm going to say that mu represents the true mean time preparing for last year's AP Stats students. Okay, so let's jump into our 4 questions here. The first one is the claim that we're going to assume to be true in order to come up with our distribution here. And we know that that's going to be the null hypothesis. So it says that the mean is 12. So I'm going to say here the claim is that students averaged 12 hours preparing. Okay, that's the claim that we're going to assume to be true, that 12 is actually the true mean for the whole population of all AP Stats students. Now, the statistic is the observed result that we got from our sample here, and we know that that is 11.4. Making sure that I'm using the correct notation here, this is a sample mean, so I'm going to use X bar, and the statistic here is that X bar is 11.4. Now, does that provide some evidence that the true mean is less than 12? Well, sure it does, right? 11.4 is in fact less than 12. So we do have some evidence that the true mean is less than 12. But do we have convincing evidence? Or could this result have happened purely by chance just because it was a random sample? Well, this is why we need a p-value in order to answer that question. So let's jump over to the picture here, the distribution. And first, I want to make sure that we recognize that this here is the sampling distribution of X bar. In other words, what are all the possible X bar values if we were to continuously take random samples of size 20 from the population, assuming that this claim is true, that the true mean is 12? So sure enough, you see that the mean of the sampling distribution is the mean of the population under the assumption of the null hypothesis. Now, the next thing we need to do is to identify our statistic here, which was 11.4. That's this value right here. That is our statistic based on our sample of 20 students. And in order to get the p-value, we need to know how likely is it that we would get that value for the statistic or farther from what's expected. In other words, we want all of this area underneath the curve. So there is some calculations that need to be done here, but that's not the focus of this lesson. So I'm going to tell you that the calculator gave me a t-test statistic of negative 0.72, which means we're about 0.72 standard deviations or standard errors below the mean. And the calculator gave me a p-value here of about 0.24. So let's see if we can interpret that p-value here. And just like we did in the first 2 examples, I'm going to start with my assumption. And here we are assuming that this claim is true. So we're going to assuming that last year's AP Stats students spent an average of 12 hours preparing. And if we wanted to write that in symbols, we know that's, of course, our null hypothesis. I'm just going to put that in parentheses here, that the true mean is equal to 12. Now let's get to the interpretation of the p-value. There is a 0.24 probability. And now let's look at our picture. Look at the shaded region that we have there, which we know is our statistic of 11.4 or lower. So let's put that into words. There is a 0.24 probability of getting a sample mean of X bar equals 11.4 hours or less, right? Because we're going to the left here. That's important. Purely by chance. Now, for this one, the p-value is fairly large. 24% of the time when you take a random sample of 20 students, you're going to get an X bar of 11.4 or lower when we assume the null hypothesis is true. Well, that very well could have just happened purely by chance. So do we have convincing evidence for the alternative? No, we do not here. And that's because our p-value is large. 0.24, which I'm just going to say is greater than a traditional alpha value of 0.05. So we do not have convincing evidence that the true mean is less than 12. Okay, this leaves us with one more example problem to go through, which would be likely a little bit later in the course, probably something you covered right towards the end of the course. Here's what it says. A curious AP Stat student wonders if the proportion of Reese's Pieces that are orange is different than the proportion of Skittles that are orange. Suppose she took an SRS of 50 Reese's Pieces and found that the proportion that are orange, P1 hat is 0.42, and an independent SRS of 100 Skittles and found the proportion that are orange, 0.20. So let's start again with our hypotheses here, just to make sure we have those written. And so we've got a null and an alternative. Very clearly here, I can see that this problem is about proportions and that it is a two-sample problem. And so I know that my hypotheses are going to be about the difference between the two proportions. And we know that the null hypothesis would say that the two proportions are equal, which would mean that the difference between the two proportions is equal to 0. Now, to get our alternative, we have to look back at the wording of the question here. And it says different than. So we don't really know if it's going to be higher for Reese's Pieces or higher for Skittles. This is a two-sided alternative, which says not equal to 0. Now, we do need to clearly identify our parameters here. So I'm going to identify P1 as being the true proportion that are orange for Reese's. And P2 is going to be the true proportion that are orange for Skittles. Okay, so now let's get to the claim that we're going to assume to be true in order to come up with our picture here. And that claim we're going to assume to be true is the null, which would say P1 minus P2 equals 0, meaning that the two proportions are equal. So I'm going to say the claim here is that the orange proportion is the same for Reese's Pieces and Skittles. That's the claim we're going to assume to be true. Now, the statistic is the observed result that we got from our two samples here. And so what we're looking for here is P1 hat minus P2 hat, which we can calculate very easily as 0.42 minus 0.20, which is going to give us a difference of proportions of 0.22. Now, does that provide us with some evidence that the alternative hypothesis is true? Well, the alternative says that it's not equal to 0. And sure enough, when we took our samples, we got a difference of proportions that is not equal to 0. So that 0.22 difference in proportions that we got there isn't equal to 0, which gives us some evidence for the alternative. But do we have convincing evidence, or could this result have happened purely by chance? Once again, this is why we need the p-value. So let's move over to the picture here, and let's first identify what this distribution is. Once again, this is the sampling distribution, but this time it's the sampling distribution of P1 hat minus P2 hat. And because we're assuming the null is true, you will see at the very center of the distribution is our null hypothesis that P1 minus P2 is in fact equal to 0. Now let's identify our statistic from the samples. That statistic is 0.22. Well, that value is right about here. That 0.22 is our statistic. But remember that this was a two-sided alternative, so we need to do the same thing on the other side of the distribution, which is just negative 0.22. And now to get the p-value, I need this area over here in purple, as well as this area over here in purple. So I did this on the calculator, and I'm going to give you the results. The z-test statistic for this was 2.85, which means we're 2.85 standard deviations above the mean, pretty far above the mean, which tells you the p-value is going to be pretty small. And even when I take both sides, right, and I add those two areas together, I get a p-value of 0.004. Very small p-value. So let's see if we can interpret. Same sort of setup as before. we need to start out with our assumption to be true. So what we assumed here was that the claim was true. So assuming that the orange proportion is the same for Reese's Pieces and Skittles. And then I'm going to put in parentheses like the more formal way of saying that, which would be P1 minus P2 equals 0. And now let's get to the interpretation of the p-value. There is a 0.004 probability of getting, now let's look at our picture here, of getting this or greater or this or lower. So we have to accommodate for both sides of this distribution here. So I'm going to say of getting a difference of sample proportions of P1 hat minus P2 hat equals 0.22 or farther from 0. So that's taking care of both sides of the distribution here, 0.22 or farther from 0. And then we need our purely by chance. Now, because this p-value is very, very small, very, very unlikely to happen purely by chance, we have convincing evidence against the null hypothesis and in favor of the alternative. So do we have convincing evidence? Yes. And that's because the p-value is very small at 0.004, which is clearly less than our alpha value. So we do, in fact, have convincing evidence that the proportion of orange Reese's Pieces is different than the proportion of orange Skittles. Now, a couple summary questions here. For all 4 of those problems that we did, we had a claim at the very front end that we were assuming to be true, and hopefully you know that this is the null hypothesis. And then the last idea here, because the p-value is calculated, is a probability calculated by assuming some claim is true. Well, that's a condition, right? We're assuming that that condition is met. So that p-value, which we know is a probability, is in fact a conditional probability. Now, let me show you another way of thinking about the p-value as a conditional probability. We could think of the p-value as being a probability, so I'll use capital P here. And what it is it's the probability of getting the observed statistic, right, or more extreme, given that the null hypothesis is true. So I'm using that conditional probability notation that you learned way back earlier in the year. The p-value is in fact a conditional probability that is calculated assuming the null hypothesis is true. Now, just to be very clear here, it's the observed statistic or more extreme. So sometimes that means shading to the left, sometimes to the right, and sometimes both sides. So let's see if we can summarize, hopefully, some big ideas about the holy grail of AP statistics here, the p-value. And I'm going to go back to the 2 learning targets that we started with here. The first of which was to be able to actually calculate a p-value. That was the first learning target, is to calculate a p-value. So I'm going to give you sort of like a list of steps that you need to do in order to calculate a p-value. Okay, the first thing that we did for all 4 of those examples is we assumed some claim to be true, which we are now just going to call the null hypothesis. So we assume the null hypothesis is true. With that assumption, we can then look at the distribution where we'll calculate our p-value, which is going to be the sampling distribution. So I'm going to say draw the sampling distribution. Okay, next, on your sampling distribution, you have to identify the statistic or the observed result that you got from your sample or from your experiment. Then the next step is to shade in the distribution, and you're going to shade, generally, I'm going to say away from the center. If you were shading back over the center, that would be a problem. which you would very likely catch when you asked yourself whether or not you had some evidence, because in that case, you wouldn't even have some evidence. And then finally, once you've shaded, you want to find the area or the probability of that shaded region. So I'm going to say here, calculate the probability. So in general, this set of steps is going to allow you to calculate a p-value. Now, the second learning target, which I think happens to be the more important learning target here, was not only that you could calculate a p-value, but that you could interpret the p-value. And after going through 4 of these examples, you notice that it really sort of follows the same structure every time. So let's write that structure down here. Okay, you always start out with your claim that you are assuming to be true up front. So in this case, it would say assuming, and then you're going to put the claim there. And the claim is always the null hypothesis. So you would put that the null hypothesis is true. And this is where I like to put the context of the problem, right up front when you're stating your assumption. Okay, then the next part of the interpretation is where we get to the p-value. There is a, and then blank, this is where you're going to input whatever your p-value is that you calculated. There is a, whatever the p-value is, probability of getting a, and then you're going to have to fill in the blank here again. And what's going to go in this blank is whatever your observed statistic is from your sample or from your experiment. So of getting a statistic of, and then you're going to have to write out whatever your statistic is, maybe a x bar, maybe a p1 hat minus p2 hat. And then we're going to say or more, or less, or farther, depending on whether our alternative hypothesis is greater than or less than or not equal to from expected purely by chance. So there we have sort of like a template that you can use in order to interpret the p-value. Now, once you have the p-value, you do have to be able to turn that into a conclusion about the null hypothesis. And so this is the part that you likely know from your class already, that if the p-value is low or less than the alpha value, then we do in fact have convincing evidence for HA, the alternative, which means that we would reject the null hypothesis. If on the other hand, your p-value is greater than the alpha level, then we do not have convincing evidence for the alternative. And in this case, instead of rejecting the null hypothesis, we would fail to reject the null hypothesis. So listen, I hope at this point you understand, first of all, how important the p-value is for AP statistics. It is the holy grail, the thing we've been working towards the whole year. And it is the understanding of that p-value that ultimately leads to the conclusion that you're probably used to writing at the end of a significance test. Now, I do have a homework problem that is, of course, related to the p-value that I'd like you to try. And Mr. Murphy will check in with you on that one tomorrow. I will be back with you on Thursday this week, where we will talk about how to identify the right type of inference procedure, whether it's a confidence interval or a significance test. But you should join Mr. Murphy tomorrow at 2 o'clock, and then I hope to see you again on Thursday. Have a good evening.